see a lot of faces that are relatively new to me, and that makes me very happy. For those who don't know me, I'm Brian Somm. I'm the chair of physics and astronomy here at Washington State University. I want to welcome you to the inaugural distinguished colloquium, and this is something that we've introduced this year. We're going to have 5 days throughout the academic year with some enhanced opportunities for engagement. We had a great workshop that was given by Professor Pollock earlier this afternoon, and I can tell you, I stopped by, I was there for most of it, and there were people from the School of Education, there were people from economics, there were people from all over campus. I think it was a really great workshop, and this is the kind of thing that we want to have happen here with this series. We're always going to be having some additional things beyond the colloquium to engage our faculty and hopefully faculty from around the campus and from around surrounding campuses. Now, I just want to say very briefly, I want to make a couple of thank yous. First of all, to Diane Bender, who's the widow of Paul Bender, who's a former professor in this department, and she contributed generously for our ability to bring in some of these speakers for this series. And I also want to thank Tom Dickinson, who did a fantastic job hosting this week and also brought resources from his Boeing professorship for this particular talk and visit by Professor Pollock this week. And so without further ado, I'm going to give it over to Tom to introduce our speaker.
Thank you. Well, one thing I have to say is that I'm sorry you didn't get your sugar fit before this colloquium, but you can get it afterwards. We're going to have a reception, okay? Steve is from the University of Colorado. He received his undergraduate degree in physics from MIT and his graduate degrees from Stanford in theoretical nuclear physics. He's postdoc at the National Institute for Nuclear and High Energy Physics in the Netherlands and at the Institute for Nuclear Theory in that small town in the West, Seattle. He joined the faculty of the physics department at Colorado in 1993, and he's concentrated on physics education and research. And so today he's going to tell us how to teach these upper division classes.
Thank you, Tom. It's a pleasure to be here. I've had a great visit, met lots of interesting folks doing great things, and I just want to share a little bit about what's happening at CU Boulder and elsewhere. This is research that I have been engaged in for almost a decade now. Just to sort of set the stage, this is a picture taken in one of the classrooms that I teach in. This is an upper division electrodynamics course. It's a second semester course, mostly juniors and seniors. And this is in the middle of a 50-minute lecture period. The students, I interrupted the lecture. The students are now working on a worksheet. They spent about 10 or 15 minutes. They're working with each other. In the back, unfortunately out of focus, is an undergraduate who took the course the previous semester. We hire undergraduates at CU. We call them learning assistants rather than teaching assistants. We have those too. And he did extremely well in the class, wanted to get some teaching experience, and so when I was doing activities like this that needed a little bit better student-teacher ratio, he was there to help out. So I'll tell you a little bit more about how that all works in just a few minutes. Also, just to begin, I'd like to acknowledge all the many colleagues with whom I work, and I'm very grateful to be at a place that has a very large physics education research group. PER is just one of the many sub-disciplines in physics at CU Boulder. There's a nuclear group, a plasma group, a condensed matter group, an education research group. And our graduate students, listed some of them on the right, they are regular physics graduate students admitted into the program like all other physics graduate students, and they just choose to do their PhD research in some area of physics education studies. And we've got lots of postdocs and basically our soft money research scientists in the group. And we have lots of collaborations with the School of Education. So many of the projects that I started off with, not the one that I'm going to be telling you about today, were collaborations with folks in other departments. And funding sources, yeah, this is the slide that we all use in the group. So I don't get all that money. Mostly the money that that supports the research that I'm going to be telling you about today comes from the National Science Foundation, a number of grants from them. Okay, so let me try to give you a little sense of where I'd like to go in our almost hour today. I'll give you a little bit of background. There's lots of education research in physics that is aimed at the introductory physics level, university level, so Physics 1, Physics 2. And I'm going to say a few words about that because I think it's relevant background, but I'm not going to focus on it. If people are interested, talk to me afterwards and I can tell you about what's been going on. But I want to sort of shift gears to talk about upper division physics. And I think partly we have to just talk about why make any changes. Upper division physics is pretty much the same at most institutions as it has been for 100 years. And it worked for us. And so I don't want to dismiss that. And in fact, I think it's important to ask ourselves, is everything fine? Are there any issues that need addressing? I think when we started looking carefully at introductory physics, it became clear that there were lots of things that could be improved upon, and they have been systematically tackled, and lots of measurable improvements have been made, and the sense was maybe we could do the same at the upper division. I'll tell you a little bit about what's changing at Colorado, and just a little foreshadowing, not so much. That is to say, the curriculum, the textbook, the homework assignments are to a certain extent as they always have been. So we're not changing the character or nature of upper division physics instruction. It's small changes, and I want to tell you about what motivates them and what impacts they have. Of course, it's a physics talk, so I got to tell you about the data that we collect. And in fact, when you're talking about educational research and educational data, it's a different kind of study than when you're studying substructure of the nucleon or an electron cloud. And so it's important to look at the assessment tools, and you have to make judgment calls. Does this assessment match with your values and your interests? This handout that I passed out, I hope almost everybody got it. If not, we'll have an opportunity later to pass it out further. Says something about what University of Colorado faculty felt were their goals for instruction in an upper division electromagnetics course, which is sort of the example that I'll have in the back of my mind as I talk about upper division in general. This was the course that we started working on first, and I have the most data to tell you about for it. And I'll end with some outcomes and research questions, but this is really not a PER theory talk. This is a very practical and applied talk about classrooms and student learning in real-life classrooms. So I won't get too much into theories of learning. Just to situate, CU Boulder is a beautiful campus. I think weather is not so different from here. We have slightly bigger mountains in the background. It's a big department. So when I tell you about things that are happening at CU, you have to kind of make the mental translations and decide what carries over from here and what doesn't. We have 55 physics faculty, and then there's a separate astronomy department, which is about another 25 faculty. In physics alone, there's 350 undergraduate physics majors, and that number is a couple years old, and we've been growing, so I think it's a little bit bigger than that now. And there's 230 physics graduate students, again, separate from astronomy. So it's a big program, and when I talk about teaching upper division physics classes, when we started this study 10 years ago, our class sizes were 30 or so, and I'm going to be teaching quantum mechanics next semester to probably 85 students, so more than in this room. So it's sort of this new situation for us, a large lecture instruction of upper division physics, and that also is impacting some of the things that I'm going to be telling you about, because we're trying to help reach our students as best we can. And of course, this issue of large classes has already been tackled for ages in the introductory level. That's one of the motivations behind the research and development that happened in intro physics, was to deal with schools like here and Colorado that have really large introductory classes. In the intro sequence, just so you know, we use clickers and peer instruction almost universally. So let me ask the inverse question: who doesn't know what clickers and or peer instruction means? Raise your hand high and proud. Okay, a couple of you. So very quickly, clicker is a technology, peer instruction is a pedagogy. So clicker is a small device. You could use a colored card or a clicker with which you can vote. It's a mechanism by which students can vote on questions during lecture. The instructor can get quick feedback and make course changes based on what's happening in the room at this moment. And peer instruction is sort of the pedagogy. This is what the workshop this morning was about, that might incorporate clickers, it might incorporate hand raising or voting in some way. But the peer instruction idea is that if I was lecturing on a physics topic, I would interrupt my lecture frequently and have you argue with one another about something physics related. So you would have to make the next step in a derivation, or apply what we were just talking about to a novel situation, or answer a conceptual question about does this make some other variable, does this change make a variable go up or go down or stay the same? And so repeatedly through the lecture, not only do you get to stop and think, but you get a chance to talk to your neighbors and try to express your ideas and your reasoning, and the instructor is there listening, giving feedback, and that's the idea. And so this has been the primary pedagogical change in our introductory level physics courses all across. It's not just physics, chemistry, biology, mathematics, astronomy. We're all basically using versions of this. In the physics department, we have an extra hour a week. So we have 3 50-minute lectures in a giant lecture theater, and then there's one more class. It's not a lab. It's called a recitation section. Apparently, you don't have one here institutionally, but we do. And so in that 50-minute period, it used to be graduate student run, and the grad student would do what they wanted. Typically, they would help students by solving homework problems for them. And you can imagine that that's great for the graduate student and of modest value to the student sitting in the class, except that they got some of their homework problems solved for them. So we changed those to pedagogy that comes out of the research group at the University of Washington in Seattle. They're called Tutorials in Introductory Physics. So Lillian McDermott and company have developed some very, very well-researched materials. So the students actually buy a book, and they work on maybe a 5-page worksheet in class, and the role of the teaching assistant and the learning assistant is to circulate and ask good Socratic questions while the students are working on these tutorials. So we've been doing that since 2004, and somewhat like here, faculty at CU, physics faculty, get a teaching assignment every semester, and it's kind of a mixture. So one semester I teach an upper division course, and then I teach a freshman course, and then I teach a graduate course, right? We teach everything. And so faculty are cycling through the introductory courses. So most of the teaching faculty at the University of Colorado have experienced clickers and peer instruction and these tutorial environments at some point. And so as they move back to an assignment in the upper division, these ideas about teaching are now percolating and present. So I think it's relevant that you know about that, because that's sort of part of how and why this change happened. One other little piece of culture that is relevant to mention, starting in 2003, we began giving a pretest at the beginning of Physics 1 and Physics 2, which came from the education research community. You may have heard these acronyms like the FCI, the Force Concept Inventory. There's a whole bunch of these. We picked some to use, and you give it on the first day or 2 of the semester, and then you give it in the last week of the semester. So you can have a quantitative measure of the learning gains, and I'll show you some of those data in just a second. So this culture of giving some measurement that's always the same. It's not your exam, which of course, you know, I write my own exams. Everybody writes their own exams. And so comparing a test score from one semester to the other is almost completely meaningless unless you really look carefully at the questions, and even then it's really hard. But if you give the same test semester after semester, then it gives you some kind of handle on whether the changes that you're making, how are they impacting students. It's a very narrow test. It's only one little topical area, so you have to be careful about over-interpreting it, but I'll say more about that. Here's a plot from almost 20 years ago now. Richard Hake published a paper in the American Journal of Physics, which we all used to read. So lots of physicists saw this paper. And it was a 6,000 student survey across 12 universities throughout the United States. And the horizontal axis here is the learning gain on the Force Concept Inventory. So that's a measure of basically what fraction of the content that the students didn't already walk in the door knowing did they learn over the course of that one semester. So it's a measure of learning gain, and it's a histogram. And so the axis starts at 0. It doesn't go up to a 1 because nobody is even close to getting perfect. These are class averages, so you would need every student in your class going from whatever score they started with to a perfect score in order to be at 1 on that scale. But what's kind of stunning and really impressive for lots of physicists is that this curve is sitting there at about 25% normalized gain. So, right, students are taking a physics class. I mean, it's already a little bit shocking at the score that they get on day 1, because most of us were thinking, gee, didn't they learn that stuff in high school? I mean, the force concept inventory really looks like high school level conceptual physics. No calculations, it's sort of Galileo ideas, and velocity is different from acceleration ideas. It's pretty basic concepts, and the force concept is highlighted, of course, in the force concept inventory. Now, this isn't the entire data set. These are the traditionally taught classes, and there in blue is the rest of the data set that Hake presented in that paper. And he characterized classes as either traditional or interactive engagement. So it was just on or off, and the faculty self-reported. He did a meta-study collecting data from these many, many faculty over several years at AAPT meetings. And you can stare at the results and draw some conclusions. What are you seeing besides that blue is higher? Anything else that sort of sticks out at you? Broader distribution. Anything else sticking out at you? Bimodal, education data, right? It's actually 6,000 divided into 2 categories is not all that high. And if you're a particle physicist, you wish you had a billion times more statistics. Also, maybe an important sociological note is that the worst of the interactive engagement classes was doing pretty much as well as any traditional lecture. So I think this gave permission to a lot of physics faculty to say, I wonder what that means, right? We all have our reactions to this. Many faculty say, it's education data, it doesn't really mean much. Other faculty will say, well, I need to look at that force concept inventory and see whether it's really a good test. Maybe it's a bad test. Maybe you can teach to the test, which it turns out is very difficult to do. And there's a nice anecdote of Eric Mazur, who's a professor at Harvard, who is included in both the red bins and the blue bins because he changed his pedagogy while the study was underway. And he tried, in fact, when his class was in the red bin, he tried to tell the students the answers to all the questions, not by showing them the question and the answer, but by knowing what was on the test. He was still lecturing, and he tried to very clearly address it and didn't help much. So, a lot of people looked at this, and including myself, I looked at this data in 1999, I think, and I said, I don't believe it, not my students, right? So I started giving first the force concept inventory, and then later we switched to the force and motion concept evaluation, which is a little harder, and I'll show you those results in a sec. In addressing this question of, is it reproducible data? This is from a 50,000 student study, so now an order of magnitude more students, and it's from last year. And this is on the FMCE, which is this other slightly harder instrument. The qualitative features of the traditional versus interactive engagement classes, very much the same. There's actually fewer total numbers of classes in the red bins because not so many people are teaching in that way, but there's still plenty of classes that are taught in that fashion. One more comment. I mean, what defines interactive engagement? It's not a pedagogy. It's not a classroom style or a classroom size. It's really, if your philosophy of teaching is predicated on a theory of learning that says, I cannot put physics wisdom into your head by speaking. You have to figure out physics. You have to engage with the material and make sense of it. If I believe that, I'm not likely to just teach by lecturing all the time. I might lecture some, but there's moments when I need the students to take the active role, and that's the name interactive engagement. So some of those classes are studio style, some of them, like at Colorado, are large lecture theaters where the students are engaged in voting and talking to each other. Many different models. There's big classes, little classes. It's all in this data set. And actually that was what this paper was about, was trying to start to pick out what's different between the classes at the bottom end of the distribution and the classes at the top end. So that's a whole separate colloquium, which we can talk about if you're interested. Here's the Colorado data in black, superposed. It was one of my first PER publications, was a replication study. And we pretty much got the same result as what Richard Hake predicted. And yeah, again, lots of stories. This was a brand new faculty member. That's me. So yeah, actually, I switched from the FCI to the FMCE because, so the FCI data is not in this plot. This is all FMCE data from Colorado. I was afraid that I might be accidentally teaching to the test, so I switched to the FMCE without looking at it. And it turns out it's a very different test, so I just wanted to not be trying to make this happen. One more little comment before I move on. 3 of those semesters, so this is Colorado instruction, 20 semesters. We're using clicker questions in the lecture. We're using these Washington tutorials for an hour a week, and we've got undergraduate learning assistants for that hour a week teamed up. They train for an hour a week with the graduate students and a faculty member to learn some pedagogy. They're taking a pedagogy course. There's a lot of infrastructure there to support student learning. 3 semesters interspersed in those 20, faculty members said, I don't really like all this conceptual stuff. I want problem solving in the recitations. So we went back to the more traditional model. And those are these 3 semesters. So on the one hand, those faculty were still asking clicker questions for 3 hours a week. There was still peer instruction in the large lecture setting. The only difference between those 3 classes and the other ones I showed you was this 1 hour a week. And even there, this faculty member was doing traditional problem solving, but had the students break into small groups and work in a group structure on it. And they're ending up pretty much in the middle of the blue distribution. And these 2 are okay. I mean, a lot of schools would be pretty thrilled to have 30% normalized gains on the FMCE. And so you can decide whether that's okay or not. But of course, physics faculty are a little bit competitive. And these 3 faculty wanted to know why they were at the bottom end of the Colorado distribution. And when I pointed out that they were way above the top end of the traditional instruction distribution, that didn't help much. Yes. Okay, so that's introductory level data. And here's some pictures. That's Carl Wyman, who used to be a faculty member at CU. He got the Nobel Prize, switched to physics education research, and then left us. Went to UBC for a while, and now he's at Stanford University, still doing education research. This is our lecture, one of our 2 large lecture theaters in Colorado. This is the place down in the basement where the students are working on those tutorials. It's cheap, to build this, you got to buy 8 tables. Actually, the expense is to hire the undergraduate learning assistant, because you got to hire them and pay them $10 an hour. So this is what's happening in the introductory class, and I would say yes. Please.
You have to hire these learning assistants. What's your ratio? How many do you need?
So the sections are 28 students, and we used to have 1 TA for 28 students, and now we have 1 TA and 1 LA, and the 1 LA teaches 4 of those sections during the week. So it's sort of 100 to 1 student to teacher ratio for the undergrads. Undergrads, I mean, for those of you who are thinking dollar signs, are way cheaper than graduate students. But they're not free. I mean, right, it's still real money, and actually we can talk about that maybe afterwards, about how the University of Colorado and many other institutions have created and supported this LA model. It's got lots of wins. It's good for the LAs, it's good for the students, it's good, right? We're coupling with the School of Ed, and I like to quip that the physics department at CU Boulder has increased the number of K-12 certified physics majors by infinity, because we didn't used to have any, and now we have 3 or 4 a year, and most of them are coming through this program, right? They get the taste of teaching and they get interested, and suck them in. No, it's great. It's really important, right? We have a shortage of qualified high school physics teachers in the United States. Colorado, it's a serious issue, and so this is really a small, but who should be preparing future high school physics teachers? Don't say it's the School of Ed's job. They're doing their job. Its physics department needs to play its role too. So that's a whole other colloquium. Okay, so I and many of my colleagues began sort of talking to each other, because we were all exposed to this and we were seeing the benefits, we were seeing the data, and people started wondering whether our majors could learn better from interactive techniques adapted from introductory physics. I published a paper which showed that our majors were benefiting by measuring freshman conceptual surveys 2 years later when they became juniors. So that was a very interesting longitudinal study which showed that these transformed freshman classes were benefiting the majors. Our majors were mixed in giant classes with lots of engineers, and so there was some concern that maybe I was showing you class averages. Maybe we were addressing the average student, but not, the little gems in the rough, the physics majors. So that was a nice study that suggested that yes, the physics majors were benefiting. But then we began wondering, well, if they're benefiting when they're freshmen, does it just stop? And all of a sudden you don't need any of these transformed pedagogies because now they're ready to learn and master upper division physics. This question, could our majors learn better? So it's a pretty vague question. Learn what? And better by what measure? So that's kind of what I want to talk to you about. And also it's a conservative statement because I think physicists by nature tend to be conservative creatures. So I don't want to make a radical change. I want to adapt things that we know work and just adapt them to the upper division population and see what happens. And if that works, maybe we could, when you've only got 25 students in a class, you can do lots of different things than clicker questions and tutorials. Although now that we have 80 or 100 in upper division classes, we're back to actually maybe these techniques are the best that we can do in terms of person power. Carl Wyman had just formed the Science Education Initiative, which was his brainchild to try to get scientists talking about education like scientists. So instead of Steve Pollock going around and being an energy ball and like doing crazy things and then trying to sell it, how about if we get together and we work as a community and we try to build on each other's work so that we're not doing random walks through education space? So this was his model for how you might go about transforming courses in a systematic way. And the center here is faculty and staff, not students. So those of you who are graduate students or undergraduates, may wonder why you're not at the center of this diagram, and that's because Carl Wyman didn't put you there. But maybe you should be, and so that could be a different model for course transformation. But in any case, we decided, and we started up here, what should students learn? So Carl stood up at a faculty meeting and said, we should have some brown bag conversations, lunches, where we physics faculty just pick a class, let's talk about E&M, junior level, and let's talk about what should students learn in that class. And let's see if there's consensus. And so we'll talk about that in just a sec. After we did E&M, we moved on to other topics. Once you've had the establishment of learning goals process, then now it's local, and so it's not the physics education research folks telling you what to do, and it's not people at another institution telling you what to do. It's your department and your decision. And then you can start hiring postdocs, which is what the SCI is really good for, to help you investigate what are students learning. So there's lots of techniques. You can videotape students in class or when they're working on homeworks. You can collect their homeworks and analyze them, and exams. You can interview students. There's lots of research techniques that you can use to investigate student learning. And then finally you can go to the bottom, which instructional approaches improve student learning. So now you can start tinkering. Try something different. You can be aggressive, you can be conservative, whatever you like. And we decided to try using tutorials and clicker questions because that seemed something we were comfortable and familiar with. And then you iterate. So you've got measures of learning at this point. So you try something, measure learning, try it. It's a slow process. And over the years, we had these brown bag conversations about E&M 1, and then E&M 2, and then Quantum 1, and then ClassMac 1, which at CU is a combined course with math methods. And Upper Division Labs, Heather Lewandowski is a faculty member who took that lead. And so lots of research projects that have been involved in all these course transformations. So that's the sort of basic story about the history and development here. Let me tell you a little bit about what's different. So here's a picture of an upper division class. I think this is a picture of a quantum mechanics lecture. And of course, this is the picture we used to take. Quantum mechanics class is about the blackboard and the teacher. And I would say what changed is that this is the picture that we're really interested in, is turn the camera around and look at the students. So in fact, this is an important point. I don't come here trying to tell anybody what to teach or how to teach it. I'm not even sure if I know the answers to those questions. I'm just interested in how students learn and what are their struggles and what are the resources that are beneficial to them. I think education research largely focuses on student learning, not on teaching or teaching methods. So that's an important change. Faculty talking to each other about teaching, what a radical concept. So, I got to say, when I came to CU in 1993, Teaching is done behind closed doors, and I think this is pretty much the model across the country. Academic freedom, and I'm going to do my thing, and maybe when I'm a junior faculty member I will be politely evaluated for tenure purposes. But largely we do our own thing, which to a certain extent is great and unchangeable. But when faculty get together, it turns out my colleagues are unbelievably brilliant, and no matter how hard I've thought about teaching any course, my colleagues have better ideas than I do, and we all feel that way. And so lots of things happened when we started talking about teaching, and we discovered that although we don't agree on anything, we actually agree on lots of things. We just never agree on everything. We explicated learning goals. We started collecting student data because we'd gotten used to doing that at the freshman level, and it kind of felt good. And like I said, whether you end up at the bottom end or the top end of the spectrum, it's all anonymous and kept private. Individual faculty members can report those results if they like on their tenure and promotion packages, so people liked to have such data points. But giving some kind of test that you can give year after year after year, it's got to be not for credit, because you don't want students studying for it or cheating or looking it up on the web. And yet we want them to try their best, so it's framed typically as a final exam practice activity in one of these classes. And so we've got some data that I'll share with you. In the classroom, there's a bunch of things that you can do, all of which go by names of student-centered pedagogy or interactive engagement. The concept tests are the easiest ones, the low-hanging fruit, right? If you're a faculty member and you like to lecture, like me, as I've been doing for the last 20 minutes, right? This is just an interruption in which students get the opportunity to debate something, and you're listening and you're giving them feedback, and it's grounding, because I was fooling myself, it turned out. When I was teaching quantum mechanics, I made assumptions about what everybody knows and what everybody doesn't know. People are not blank slates. You might think nobody knows any quantum mechanics when they walk into quantum mechanics, but people know lots about quantum mechanics. They have a lot of ideas that are impacting the way they're trying to solve problems. I'll tell you a little bit about modifying homework, which was based on the learning goals that we're about to take a couple minutes to look at. And we built some tutorials. So these are longer, student-centered, paper-based activities modeled after the freshman tutorials, where you interrupt not for 5 minutes, but for 25 minutes, and you let the students work in small groups on something. So let me take a little break, because I do have this handout with our faculty learning goals. I would like you to take a minute. Who doesn't have this document? Raise your hand, please. Could I ask you to hand these out to the people whose hand is up? So the first thing is just to stare at this. Understand it's not from me. This is not a physics education research document. This was my research-focused, very busy colleagues who came to brown bag lunches and had a couple of meetings. About 25 of the 55 faculty came and contributed to these learning goals. And typically, somebody would shout out a word or a phrase. That's usually the bold ones here. The order isn't particularly significant here. This was a historical order when we were coming up with these. And then sometimes the only contribution of the PER group would be to say, could you operationalize that? How would we measure that? And so the paragraphs that follow sort of get a little bit more specific. I'm going to just give you a sec to scan. Don't try to read this document. You can take it away if you think you would ever look at it again and look at it more carefully, but I just want to give you a chance to get a sense. I got a couple more. Did anybody still not get one? Here, let me keep one and let me pass this up. So what I'm going to do is what I always do in my class. Please turn to your nearest neighbor or neighbors. If you don't know them well, please introduce yourself. If you know them too well and you don't want to hear what they have to say, turn around and talk to somebody behind you. Faculty, talk to graduate students. Graduate students, meet some faculty members. And just, do you like these? Are they relevant here? What's good? What's bad? Just a minute. I'm not going to give you very long. Not nearly enough time. You got the classic thing. You just, you can turn around. Or move. Yeah, this is what happens when people don't sit next to each other. You can talk to your neighbor behind too. Pardon? I just want your sort of reaction to these as learning goals. Do you subscribe to these? Are we missing important things? Like, what do you like, what do you not like? It's just a chance for you to look at our goals, really. Okay, folks, I'm going to do a terrible thing and interrupt these great conversations because you can do this later. And in fact, what I would love would be if people got inspired enough to call a brown bag lunch and say, these Colorado goals are crap, but we could come up with a better list. Any quick reactions before I move on? Anything that somebody came up with in your discussion that seems...
I'm curious, maybe I didn't look carefully, but one of the things about problem-solving strategies is to look at limiting cases. And I don't know if I see that advertised.
Yeah, I believe that looking at limits is in number 7, expecting and checking.
Okay, fine.
Yeah, it was definitely something that we talked about. I would say this is not the content learning goals of E&M, right? Number 9, Maxwell's equations. You might have been a little frustrated that that's it. But in fact, what happened was in the brown bag lunch, people were like, well, my learning goals are that students should be able to solve end of chapter problems in chapters 1 through 6 of Griffiths after the first semester and chapters 7 through 12 after the second semester. And we all kind of nodded and said, yeah, that's what we want. And so then, we sort of sat there and it's like, is there anything else? These are juniors. Like, are we satisfied that if you can do that, that you are a physicist, that you are becoming a physicist? That's what these are juniors. In a year, they're going to graduate and we're going to tell the world this is a physicist from the University of Colorado Boulder. And there was the sense that even if you can solve Griffith's problems, if you can't expect and check solutions, you're not yet thinking and acting like a physicist needs to in order to be successful in a career as a physicist or a professional or an engineer. Yeah.
So the thing I see on here that I think is extremely important and should definitely be on here, and at the same time it's one of the hardest things to implement and execute is communication.
Communication. So number 4. And this was pretty quick to come up in the faculty conversations. And this document proved to be very useful to me, the education researcher, because when I interrupted my lecture with clicker questions, you can bet that some faculty members said, you're wasting your time. And I said, well, no, I'm trying to tackle some of the important meta learning goals that were listed by you, including communication. How am I going to help teach students how to communicate except by having them communicate and listening so that I can give them feedback about whether their verbal communication is appropriate and right level and on target. So yeah, it's hard. A lot of these turn out to be hard to measure. The one that most faculty notice right away is number 8, intellectual maturity. That would be nice. But we talked about it, and faculty said, let's define it. Accepting responsibility for your learning, being aware of what you do and don't understand. So that's a definition. It's not everybody's definition, but it seems like a pretty good one. And then evidenced by asking sophisticated, specific questions, articulating where in problems you experience difficulty, and taking action. Those seem like pretty concrete and maybe measurable, not on a test. I can't think of a test that would measure intellectual maturity, but if I could observe students in classroom settings and in homework settings, I could probably be able to say whether I was making progress. The other thing is, when we went back and revisited these learning goals for E&M 2, you can imagine faculty were like, yeah, it's a pretty good list, are we done? And how about physics mechanics the year before? Yeah, it's pretty much the same. Oh, we changed number 5, the specifics under the problem solving, and number 9, Maxwell's equations, you fine-tune those. But yeah, this is kind of what we think it means to act like a physicist. And only recently have people in my department begun thinking about, well, what's the arc? Freshmen should be answering and improving on some of these measures, and so should seniors. So I leave that also as a question. But I'm going to move on and show you some more of the upper division results. One last change was instead of office hours, we now hold homework help sessions. The name is slightly less intimidating. You find a space that isn't your office, which some students don't like to go to for whatever reason. And in fact, it's a place for them to go and work together. And then you tell them what hours you'll be there to help out. And so it's more of a place where it's a safe space for students to work together on their homeworks. And this has proven to be enormously popular with faculty and students. It's easy to implement, and we do it at all levels. Let me tell you a little bit about some of the assessments, sort of running low on time. We tried to gather data from lots of courses. It's terrible if I make changes and then report data from my classes. We've got 9 traditionally taught classes and 9 transform classes, trying to get, you know, the old Richard Hake model of trying to get as large an N as possible, although in the upper division you can imagine it's a much slower task than at the introductory level. We're at 515, an order of magnitude smaller than that old introductory data that I showed you. We did look at some common traditional exam questions which had been crafted before the project began, because we had photocopied the semester's work from before we began the project. But we also developed an upper division electrostatics assessment. We didn't want to use the freshman electricity and magnetism assessment because they're not freshmen anymore. So I'll show you a couple of the questions that were developed. Stephanie Chastain did a lot of that work. These were also part of the brown bag lunch discussions, is what should go on this assessment. There are 8 questions at the beginning that say, don't solve the problem, just tell me your general strategy and why you chose it. So here's one. You'll appreciate this, Tom. A grounded conducting plane with a point charge Q at a distance A, find the electric field. Don't solve the problem. We'll ask that on the final. This is just a practice test. Just tell me what method you would use. So if you've taught E&M, or taken it recently, graduate students, you probably go, oh, that's the classic canonical method of images problem. And that's all we're looking for. It's like recognizing, in some cases, what is, you know, you learned a lot of methods in this course. And it's really easy to answer this question on exam 2, because that's what exam 2 is about. But it's much harder to answer this at the end of the semester when you have like 5 different ways to find electric potential. Here's another one. You're given an infinite solid conducting cylinder. You put it in a uniform electric field. Sketch the induced charge distribution on the conductor and the resulting electric field. So again, you know, this question, on the final exam, I'll probably ask them to compute the induced charge, right? Which is a complicated formula. It's separation of variables in cylindrical coordinates. It's an exercise in vector calculus. But this is not asking them to do that, because I figure if you can do that, you should surely be able to expect the answer, right? Positive charges go one way, negative charges go the other way. That's all we're looking for. And most of my colleagues reacted to this test in the same way that we all as a community reacted to the force concept inventory. We rolled our eyes and said, give me a break. If they can compute that, of course they can sketch this. I mean, that's like the trivial. Well, never use that word, right? Right, don't forget that the students have learned electrostatics, but they've also learned magnetostatics, and they got to keep them separate in their mind at the end of the semester, so maybe slightly less trivial than it looks. Here's the scores. The horizontal axis doesn't mean anything. It's just classes 1 through 9. The blue line is the average weighted over individual students. Sorry that the left-hand scale got cut off. This is the score on the post-test. Average score 45%. So, okay, that sounds like dismal failure. And many of my colleagues, and maybe even me, I was expecting something a little bit higher than this, because the average on my exams in the class are like 75. That's kind of how I calibrate my exams. I'm going to slide these data over and add in the ones in which we used clicker questions and tutorials and modified homeworks. It's an improvement. It's not quite as big of an improvement as you might have hoped for, but it's 12 points on a, 12%. That's a full letter grade better on average with some noise, including some at CU and some not at CU. Here's an interesting, important data point. I gave the test to the incoming graduate students, and here's their score. So now all of a sudden, it's looking really more impressive. Right? Some of these classes, the average undergraduate at CU Boulder is doing as well as the average income, our graduate students at CU Boulder are really remarkable, right? Cream of the crop, topped in the United States. We got 4 Nobel Prizes at CU Boulder, right? So that seemed like, rather than shooting for 100%, which is arbitrary, how about shooting for, you know, a really awesome goal, which would be having our average students perform the way incoming graduate students perform. I'm going to represent these data so that the horizontal axis is actually the score. So this is now a histogram. So that's the same data set. And all of a sudden, you know, that old Hake result is just staring you in the face. Interactive engagement does a sigma or more better. It's like when educational data separates by more than a sigma, that's a really good result. It's hard to do. Now, I told you that we had given also conventional questions, because this is all conceptual questions, right? Like I was just showing you. So let me show you quickly some of the results from that. 5 exam questions graded blindly, so the students from the Professor White's class is a traditionally taught class. That's before any of this stuff happened. You can ignore the blue class because that's me, but you shouldn't ignore the purple class because that's a junior faculty member who's teaching E&M for the first time at the upper division and came to me and said, hey, I hear that there's these materials, can I use them? And I said, sure. And he's like, great, that'll save me a lot of effort in creating a class for the first time. So the first thing that we did was just grade the questions for correctness. Now, on the exam, when the instructors grade these questions, we give lots of partial credit for, you know, good try. But this is really just grading, did you get it right? And it's about a 60% average, and it's indistinguishable across the traditionally taught class and the transformed class. So that's good news, I would say. In education research, what you don't want is to break something like traditional, you know, calculational skills. This wasn't what we were targeting. We weren't really expecting to see an improvement, although we had kind of hoped that if you knew how to solve a problem and could check it, maybe you would do better on the calculation, and the answer is no. On the other hand, we went back and regraded those same questions looking at different criteria. We looked at explication of reasoning, communication skills. Did the students write words next to their equations? Did they organize their page? And now there's a big difference, because in the transformed classes, we're talking about that all the time. And we didn't change the exam questions. They're photocopies of the old original exam questions, so the students are spontaneously sharing their reasoning on exams for us. We regraded them one more time, because we were looking at those learning goals. And another one of the learning goals was expecting and checking answers. So we looked, never mind whether they're correct, never mind whether they presented clearly, did they indicate on the page that either before they started or after they were done, they did some kind of sense-making or prediction? And again, marginally statistically significant improvement from Professor White to Professor Purple. And my students, I don't know, I'm too energetic and they get all excited and learn stuff. Okay, so this looked to us like a very strong success story. Improved qualitative conceptual scores, no loss in calculational skills on those questions, and improvements in other of our learning goals. So, this is sort of the bottom line where I kind of want to leave things off. Just so you can see a flavor of what does an upper division concept test look like. I've got a couple for you. So here's an E&M concept test. Which of these could be a static physical electric field in a small region of space? I'll give you a hint. This is on the board. So, this is a great question. Students at first are all over the map, and then it sort of starts percolating around the room. You're looking for curl, because I've just told them there should be no curl. And then the question that goes around the room is, well, does that or does that not have a curl? There's no formula to compute. They can all compute curl. But they're looking for curling, because that's the word. But some people remember from their math class that if this was a fluid flow and you dropped a little pinwheel, it would spin, and so that goes around the room. And then, all of a sudden, you think, okay, they're done, they're going to get this right. But then the conversation switches to, well, this one doesn't have a curl, but how would you make it? Wasn't what I was asking, but that's what people were asking. And year after year, this question generates that conversation. Where does that field come from? I thought we were done with del dot E equals rho over epsilon naught. We're moving on to voltage and potential. But it's a great physics-math connection as well as multiple representations. It's achieving lots of my learning goals besides computing. That's the histogram from the class. It's a hard question. The D field, I don't know if that makes you swallow a little bit. If you haven't taken E&M in a while, you forget that and then you relearn it. Where is the D field discontinuous? Hint, del dot D is equal to rho free. Helps answer this question a lot. That's also on the board, but still, there's a lot of debate and discussion about this. So the connection of the math to the physics, you need to be able to do this. This is boundary conditions. You can't solve the math if you can't answer this question unless you're just following some mindless template. Here's one more from a quantum mechanics class I took last semester. In the middle of a derivation, I get to the line at the top and I just pause my Blackboard derivation and I say, please simplify the left-hand side. So if you haven't taught quantum mechanics, this might not make a lot of sense to you, but EK and EN, it's an orthonormal set, so this becomes a Kronecker delta on K and N. We're summing over N, the sum collapses. But the students have to make a bunch of decisions at this moment. Does it collapse to the symbol N or to the symbol K? Or does it leave a sum behind? To me, this is basic stuff, and it's essential to move on. It's Fourier's trick. It's the whole idea of Fourier series. It's used in E&M. It's used in quantum mechanics. It's used all over the place. And I really wanted the students to just have a moment to think and discuss and generate it for themselves, and then we can move on. They actually did quite well on this question. But B and C was a dispute. How do you collapse the sum, and what symbol is left behind at the end? It's really important that you get that right. Here's a modification of the homework. Consider the field E is C R vector over R squared. Note that's R vector, not R hat. So it's not the Coulomb field. And Griffiths asks this question. Most of my questions come from Griffiths, but I disguise them. And in particular, I add stuff. So Griffiths asks part B, calculate the divergence in curl, test your answers using the divergence theorem and Stokes theorem. It's a math question. And I tried to turn it into also a physics question like, sketch it. What are the units of C? What charge distribution would you need? Describe it in words and formulas. And I had to end it with, is it physically realizable? Because I believe the answer is no. This is a nonsense field. Maybe you could produce it locally. You certainly can't produce it globally. It requires infinite charge densities. But that's okay, right? We're physicists. We can deal with abstract mathematics, but I want students to also realize there's physics questions and math questions, and we need to be able to talk about them both. So one last piece of data. In the upper division at Colorado, so these are the upper division courses, mechanics, E&M, quantum mechanics, and the axis to the right is time. So that's SF is spring, fall, 2004, 5, 6, 7, 8. So each box is a semester, and I'm going to put a check mark in the box if the faculty member used clickers and peer instruction in their class. Not because clickers are necessarily great or magical, but just as a marker of maybe there's some kind of modified pedagogy going on. So in the old days, yes, there was a couple of us. The blue star was Michael Dobson, who's a PER faculty member. He created a bunch of nice StatMech questions. I was at a Christmas party right here and told this professor, and he's like, oh, cool, I'd like to see Mike Dobson's questions. He liked them, he used them. This is a condensed matter theorist who passed it on to his colleague, who passed it on to the colleague. So this is 4 different faculty members. This is one person who taught freshman physics and really liked clicker questions and went to Mike Dobson and said, maybe I could do this in mechanics. So he helped her write a few questions, and then she took over. She taught Mechanics 2 and then Mechanics 1. This was the state of affairs. It was a few energetic faculty members who thought this seemed like a cool idea. And then comes Carl Wyman and the brown bag lunches, and the SEI got us a postdoc, and I got an NSF grant. And that's the phase change that happened at CU Boulder. So not that this will happen, but that this can happen is, to me, kind of inspirational. And you can be the optimist and see the glass is half full, or the pessimist and see the glass is half empty, because it is half empty. Half my colleagues are going to have, they're not going to touch this with a 10-foot pole, and that's fine. We never had a faculty vote. There was no executive decision to do this. This is individual faculty members choosing to teach their course how they like. So I will end here. I'm happy to entertain questions. I don't think I want to talk about this, so this is a great place to stop. Lots of changes happening. I would say, it's a slow but steady progress. And the data that I showed you was not meant to say, hey, you should use Colorado materials, although they're all free and available online. In fact, let me just show you the, sorry. this is an other talk. There we go. If you want, you can take a look at clicker questions and homework problems. And my advice to faculty is take what seems relevant to you and your learning goals and your students. And we love to get feedback. If it works, if it doesn't work, we can add to these databases. And let me stop here. Thanks for your attention.
Take some time for a few questions.
Yeah, a couple questions. First of all, that last with all the check marks, are all of the questions that people are developing then available at these places?
So yes, all of those questions, if the faculty members gave them to me. So, and most do. The blue stars here represent PER faculty, and so those are definitely all sort of carefully annotated and put on the web. So you can actually see on all the ones with the blue star at the bottom of the slide, you can see what were the scores for 3 or 4 semesters at Colorado on the clicker questions so that you can know whether our students found them to be easy or hard. But some of those others, like ENM2, those were just faculty members, and actually I asked them for their questions and then used them in my research project. In Quantum 2, one faculty member has donated their questions and it's on the website. So, yeah.
It seems to me, to finish that out, is that it's hard work, I find, to come up with these kinds of things. Having to do it yourself is very, very intimidating. So you really want to have a huge trove.
Right. So I strongly agree with that, and I would love to build these up and then have them, have a system where they can be ranked and evaluated. You could like the questions or not like the questions. I haven't worked on that yet. So right now it's all, this is like lower division PER in the early 1990s, right? We're just starting in the upper division. There's not that many people working on upper division transformed pedagogy, so you got to really hunt around for resources. Let me let you pick people.
Okay. So I was wondering if to get repeatable results, you need to use the same questions for pre and post tests. But then the calculation questions become like, oh, people know that it was on the test last year, so how do you like, I can see doing the pre and post test, but how do you switch it up so you don't have to worry about students?
So the pre and post test that we use in the freshman level, it's a different model in the upper division. Mostly, in some of the classes, we only give a post test, like quantum mechanics, because the pre-test turns out to be just a disaster. We actually have a different version, so the model is different at the upper division. We give a pre-test in ENM, but what I was showing you was not the gain. It was just the score on the post-test, because we kind of decided as faculty, that's really what we care about. And we give a simplified version of the pre-test that we think was not unreasonable. They were things that in principle you could have learned as a freshman, just to get a kind of a gauge of whether, what you want to be careful of is if you give the tests at very different institutions with different student populations and one institution gets a high score, is it just because the students walked in the door with a really different preparation level? So we just want to be able to control for that. So we're not actually doing the learning gain game. Your other question about whether students look at pretests to study, so these are given in class and then they're collected and never discussed again. No solutions are posted ever for the pre-post testing, and it's just, these are just activities in class. We do lots of, right, these are transformed classes. The traditional faculty who give them have to frame it as, I'm curious about where you're starting off, so we're going to spend 20 minutes doing this pretest, and at the end they say, well, maybe this would be helpful in your beginning of preparation for the final exam to think about some of the concepts that we've been talking about.
So you don't use any like calculation questions, or like when you said you evaluated communication by how they organized their problems, right? Or
yeah, so those 5 questions that I told you about were exam questions taken from an exam, and that study was done once and never repeated because we didn't want those questions to get out and students would know that we were going to ask them over and over again. So that was sort of a single shot attempt to just make some claims about traditional problem solving. It would be nice if we also had traditional problems, but it's tougher to give them. You got to kind of give them on final exams, and then they're for a grade. Sorry.
Have you done any longitudinal studies about the transformed classes and how that affects your undergraduates' GRE scores?
The quick answer is no. Those studies are really hard. I can't get access to GRE scores unless the students send them to me, and we haven't really tried that. It's an interesting question whether these course transformations would impact GRE scores. It's possible because the GRE is adding a sort of, there are questions on the GRE now that have this flavor of concept tests. Some of them are computational, some of them are more like this. But no, we really haven't done that. And longitudinal studies are so hard in education. So, you know, our major's exploding in size. As I mentioned, these classes were 25 when we started this project and 80 to 100 now. So it's certainly popular, and we're not having any anecdotal complaints that students from Colorado are having a harder time getting into big-name graduate programs. But again, we don't keep any statistics on that, so it's really, really hard thing to measure.
One more quick question? John?
So I'm kind of in the EM, but I'm coming at it from an engineering background.
Okay.
And with engineering, we're ABET accredited. And if you look at what ABET requires of us in all our courses, there are student learning outcomes, and they aren't, you know, too far out of line with what you came up with.
Right.
You know, sitting around and discussing this. This is ability to communicate lifelong learning, understanding in a global and societal context, ability to work in multidisciplinary teams, you know, ability to design within constraints and all these other things. So it's interesting to see kind of that alignment.
Yeah.
But you know, sitting here with my engineering hat, I don't see anything here that doesn't translate to many, many other disciplines. So, you know, you're talking with this physicist hat on. I just wonder if you have any words to say about translation across multiple disciplines.
Yeah, I wish every discipline would engage in this kind of research so that we could improve, you know, educational system across the board.
I
Look,
wish all engineers would become physics majors.
no, I wouldn't say that that's our goal. You know, look, in a certain sense, to boil down what's happening here, faculty got together and talked explicitly about their learning goals, which sort of seems like a no-brainer that we should be doing this. And then we're slightly restructuring our classes so that there's opportunities while you're teaching to hear student voices. Again, like, how could you imagine teaching successfully without constantly controlling for where the students are in fact at rather than where we wish they were at? And I would say that's the bulk of this research. But then, of course, there's all the actual materials like the homeworks and the clicker questions, which, as was pointed out, is a tremendous labor the first time you go through it.
Okay, so I'd like you to join us at the reception, which is going to be up in the lobby here. We're going to take Steve and throw him up there. Just ask him all kinds of questions. Thank you, Steve.
Thank you.